Of the four subfields of anthropology, two have very similar methods in collecting data and doing fieldwork, and these are physical anthropology and archaeology. So in this video, I want to talk a little bit about how we go about collecting our information when we're studying either the evolution of humans or the cultures of past human civilizations. We first need to look at a little bit of the history to situate ourselves to appropriately understand where anthropology and where archaeology and physical anthropology are really based. Okay, so throughout human history, people have understood the world that they lived in, typically according to religious belief systems. And certainly this was the case in Europe and in the United States throughout the 17th and 18th centuries, up until the early 1800s. So most of what people believed about the origins of humanity and the beginning of the earth was based on the biblical account of the creation of the planet. So most people believed or understood that the earth was created by God, and he created the heavens and the stars and the earth and the seas and the land masses, and created all the animals and eventually created man, and then on the seventh day he rested. This biblical account was the framework by which people understood the world that they lived in. They also tended to believe that the earth was approximately 6,000 years old, based on the time in which they were living and, the biblical account, the biblical chronology that had been set forth in the Old Testament. 6,000 years old seemed like a very appropriate age for this earth. They furthermore used biblical stories to account for things that wouldn't be accounted for in just the creation story. So particularly the account of the flood, Noah's great flood, that was thought to have changed some landscape features. Perhaps the flood carved out canyons, certain places in the earth, and it pushed up mountains in others. But for the most part, people understood that the Bible gave a true telling of how the earth came to be the way it was to that point. And people really took this to some extremes to try to pinpoint the exact date of creation, the date of the origin of the earth. And James Ussher is one of those people. There were many individuals who tried to calculate the date that the earth was created, and he was one of them. He was an Irish archbishop, and so he used the Bible to calculate backwards in time when God first created the earth, by adding up all of the dates in the Bible, setting year zero as the date of Jesus' birth, and then working backwards through the Old Testament. Using some corroborating historical documents and all of the lineages that are preserved within the books of the Bible, James Ussher eventually settled on the date of October 22nd, 4004 BC. Right? He managed to get it down to an exact day of a month. And furthermore, he said that the earth was created at 6 p.m. and it was a Friday. That's an incredibly precise date for the creation of the earth. But again, it fit within what people already believed, because 4004 BC was about 6,000 years ago. So it all came together in a way that made sense for the majority of people who ascribed to the Judeo-Christian tradition of creationism. However, there were people existing in the world at that time who weren't necessarily contradicting religious belief, but were very interested in how the natural world functions. What are the natural processes that we can see in action in everyday life? So one of these people was Nicholas Steno, who lived in the 1600s. Today we would call him a geologist, but at the time there was no such thing as geology. But through his observation of the natural processes of the earth, he developed two laws, which we would now say are geological laws. These are superposition and original horizontality. And while he couldn't have predicted it at the time, these two geological laws form the foundation of most of the rest of geological study. So we really owe a huge debt to him. And it's important for us to talk about geology and also paleontology, which is the study of animals that are no longer living, because these disciplines are really where anthropology and archaeology first got their roots, got their disciplinary basis. In the late 1700s, there was a man named William Smith who was living in England, and he wasn't a particularly educated man. He was actually more of a day laborer. The late 1700s in England was a time of the Industrial Revolution. It's when society was really starting to change as factories were being built up for the mass manufacture of material goods. And so with all these big factories being built up all over the English island, people were flocking to these factory centers, but they also needed fuel to power these machines. And so the fuel that they were using was coal. There's a lot of coal naturally available in England. The problem was that coal wasn't necessarily where the factories were. So after the coal was mined, it needed to be shipped to the factories. In the 1790s, there were no such thing as automobiles or trains, and so the only option for transporting coal, at least over land, would have been taking it on horse cart. But that takes a lot of energy to use a horse team every time you need to deliver a load of coal. It's actually much easier if you can find a waterway to simply float coal from one location to another. So the people who were mining the coal and transporting it to factories throughout England, they did utilize these natural waterways, all of the rivers that cross-cut the country, but they also dug a lot of canals, large ditches that they could float the coal from one place to the next. So William Smith was employed as a canal digger. He really was a manual laborer who was employed with the task of digging these canals so that coal could be transported. As he was digging these canals, though, he started to notice something. So as he would dig, he'd be, starting at the land surface, and he'd start to dig down. And what he found was that he would find a layer of earth that had a certain type of nodule in it. And that same type of nodule would exist throughout that particular layer of earth. Below that layer would be a second layer with a different type of nodule in it, and so on, and so on, and so on. Now today, we know that these weirdly shaped nodules are fossils. They're the fossils of tiny creatures that lived millions and millions of years ago. But at the time, people didn't necessarily have a great understanding of what a fossil was. Anyway, as he would dig, he realized that he could find this succession of layers of earth or layers of rock in exactly the same order all across the country. And so this got him thinking about what that was supposed to mean. If he could find the same layers of earth with the same types of fossils in them from place to place. He finally was able to put it together and realize that probably these layers of earth had originally extended across the entirety of the English country, and that they likely represented events in time where layers of earth had been laid down or deposited. He further started to realize that for this many layers of earth, this many distinct layers of earth to be laid down one on top of another, there had to have been a pretty significant time depth associated with it. So this first started to call into question the idea of an older Earth, an Earth that might be more than 6,000 years old. Around the same time, a man named John Frere was living in England, and one day while digging a pit outside of his house, he found a lot of animal bones, and they were the bones of animals that did not exist in England at that time. Things like rhinoceros and mammoth and lion. And if you know anything about England, it is not the climate for lions and mammoths and rhinoceros. Mythical creatures who made them. Today we know them as hand axes, and we know that humans or human ancestors made these very far in the past. But at the time when John Frere first found them, that was not the understanding of their origins. However, because he found these particular stone tools in very close association with the bones of animals that no longer existed, he suggested, and really for the first time, that there existed a time in the past when humans didn't know how to work metal, and the only types of tools they had were made of stone, and that there existed at that time animals who are no longer alive today. and that because of these differences, because these are such vast differences from the world that he knew, that there must have been a time far, far, far in the past when man existed alongside these animals. And so he really did push the antiquity of the Earth back much, much further than 6,000 years ago. This was a revolutionary idea, and finally people were starting to get this accumulating evidence to suggest an older Earth. In 1830, the first book on geology was published, and that's not very long ago. So our understanding of the natural world is a relatively recent phenomenon. In 1856, a huge discovery was made in Germany when some road diggers found this particular skull fragment. Now, as you can tell in the photo, this skull has some very, very pronounced brow ridges. So the part sitting right above the eye socket. For the German workers who found this particular skull, they only knew of one type of hominin who possibly existed on the Earth, and that was us, humans. So it never occurred to them that this could be anything other than human. However, noting the very thick skull and the very pronounced brow ridges, the people who found this skull made some assumptions about the likely intelligence of this person, and were employing some very ethnocentric and perhaps racist ideas about how humans vary across space. And so they said, well, this is probably the skull of an individual who's not very smart. This is probably a Russian, because the Germans, they didn't like the Russians very much. So they figured this was the skull of a Russian who had fell in a hole and had died. Stupid Russian. Turns out it's not a Russian. This is the skull of a Neanderthal, and it was the first hominin species, the first non-human hominin species ever found. Unfortunately, it couldn't be understood at the time that it was first discovered because there wasn't a framework to explain how there could be species other than us who existed in the past. And it wasn't until 1859 when Charles Darwin published On the Origin of Species. And in that book, he brought us the theory of evolution through natural selection, the idea that animals, that animal groups and animal species change through time. And you'll see this image here. This is Charles Darwin's first evolutionary tree, and it looks very similar to that cladogram that we drew earlier, with the branching of different groups off of ancestral nodes. My favorite thing about this, though, is this little quote up in the corner where he says, "I think," because he was still working through these ideas himself. Today we understand evolution is a very robust theory, and in science, a theory is it doesn't mean that it's sort of iffy, it doesn't mean that it's unproven, it just means it's the best working explanation for all of the evidence that we have, and it has never been disproven. But at the time, these were still ideas that he was working with, that he was modifying, and it was a pretty novel idea. So the development of geology and of paleontology set the stage for archaeological discovery and for then eventually the field of paleoanthropology or physical anthropology. And so a few of these geological laws are very important to us when we go about collecting our data. The first of these is the law of superposition. And this again was first recorded by Nicholas Steno in the 1700s, or 1600s rather. The law of superposition states that layers of earth are deposited sequentially one on top of another, so that the layers of earth that are lowest in a sequence are older than those at the top. So it's a way of chronologically ordering layers of earth according to their position in a sequence. The word superposition, super meaning above, and position meaning position. So if we consider these three layers of earth, these three strata, and strata just means layer, strata number 1 will be the youngest because it is on top, whereas strata 3 is the oldest because it's on the bottom. The second geological law we have is the law of original horizontality, and this states that these strata of earth are originally deposited horizontally, or flat. They're laid down flat. But when we see that layers of earth curve in some sort of way, or show some sort of geometry that's not completely flat, It's because after they were laid down, they were then deformed in some way. And with this particular instance, it's most likely that these layers of rock were all laid down flat and then were compressed over time, which caused them to curve upwards. Our third very key geological law or geological theory is that of uniformitarianism, which is an unfortunately complex word, but very, very important to us. Uniformitarianism is the idea that the processes that we can see occurring in the natural world today have also occurred in the past, and they will continue to occur in the future. If we think about something like gravity, we know that gravity is constantly working. It's constantly there. We don't need to get up every day and test whether or not gravity is still present. It's always going to be there. If we drop something, it's always going to fall to the floor, because that's how gravity works. Now, because we know this to be true of our everyday lives, we can also push that into the past and say that gravity also existed in the past, and it had the same effect on objects in the past as it does today. And we can further surmise that gravity will continue to have these same effects in the future. So gravity is not something that's going to change from one day to the next, and it's not likely to change from 1 year to the next, or from 1 million years to the next. Uniformitarianism says that we can use today to understand the past. So with all of these geological laws, we can now turn to how we start to interpret the material that we collect, or how we can start to put some meaningful information together regarding the types of, regarding the materials that we'll find as archaeologists or physical anthropologists. So obviously time is a big factor for us. As an archaeologist, if I find a really cool stone tool, it's going to be very important for me to determine exactly when that stone tool was made. Was it 500 years ago? Was it 50,000 years ago? That's going to really sway my interpretation of it depending on what the date of that object is. So there are a few ways that we can put dates on objects, and there are two main types of dating programs, and we call these relative and absolute dating. Relative dating is when we use the law of superposition to chronologically order archaeological sites or archaeological artifacts or layers of earth based on their relative relationship to each other. So for example, if we have again our layers of earth here, the law of superposition tells us that the layers at the top are younger and the layers at the bottom are older. Now by correlation, the fossils in this bottom layer will be older than the fossils in the top layer, because relative dating tells us that artifacts or fossils found within layers take on the same general time range as those pieces. So relative dating tells us older than or younger than, but it doesn't give us an exact number age. And that's where absolute dating comes in. Absolute dating puts an exact number on archaeological sites or artifacts or on strata. So absolute dating can tell us this thing is 300 years old or this thing is 5,000 years old, or in this particular diagram we could say this strata is 1.4 million years old, which means that this fossil is also 1.4 million years old. We can say this strata is 5.2 million years old and this fossil is 5.2 million years old. And we can also use relative dating and absolute dating together. Okay, we can combine them to get even more information out of this particular sequence. So if we know that this layer 7 is 1.4 million years old, and that's what MYA stands for, million years old, and we know that at the bottom this strata is 5.2 million years old, we know that the layers in between have to be older than 1.4 million years old because they're below that layer, but they also have to be younger than 5.2 million years old. So even if we can't get an exact date for those strata, we can get some sort of relative date based on the absolute dates above and below. One of the specific methods of relative dating that archaeologists use is called seriation. So let's just return to our three strata here and imagine that each one of these stars represents an artifact. Which one of these artifacts is the oldest? It's artifact C at the bottom. And so the youngest would be artifact B at the top. That's pretty straightforward. But let's add a few more artifacts in here. If we look at artifacts E and C, it should be pretty clear that since these two are in the same strata, they're probably about the same age. But let's think about artifact F. Which other artifact is artifact F most closely related to, or most similar to in time? It might be tempting to say that artifact F is similar to artifact D because they're so close together vertically. But because of the law of superposition, it's actually artifact B that F is more similar to because they both exist within the same strata. So because this strata was all laid down at the same period of time, then these two artifacts would have also been laid down at the same time, whereas artifact D and artifact A are more similar in time. So if we manage to be able to connect strata across long geographic spaces, we can use the theory of superposition to understand the relative ages of lots of different types of archaeological materials. But we are not always so lucky in archaeology to find sites that are connected by similar strata. So we have to develop a different theory or a different practice to be able to chronologically order a number of different sites that are disconnected by strata. So let's say we have these 9 sites, A, B, C, D, E, F, G, H, and I. They don't share strata, so we can't use superposition to order them chronologically. What do we do next? Well, this is where we turn to the method of seriation. Seriation uses the relative frequency of artifact types to order sites chronologically. And it's based on the theory that when an object is first introduced to a society, when a certain tool or a certain piece of art is first invented, it won't be very common in the population. In fact, there will only be a few of them. But eventually, it will start to increase in popularity, which means more people will start to have them. So there will be more of that object in the population. Eventually, though, that popularity is going to fade, and so the artifact frequency will decrease again. So this creates what we call a battleship curve, where we see a slow start, an increase in popularity, and then a decrease in popularity. And a good example of this can be seen if we look at the popularity of VCRs and DVD players here in the United States in the last 50 years. So now let's go back to these 9 archaeological sites that we had on the map from before. Let's imagine that we excavated each of them. And from all of these sites, we've collected a certain number of artifacts. Altogether, there are 3 different types of artifacts. There are hand axes, which are the oldest type of artifacts, so those existed before anything else. There are ceramic bowls, which are the second oldest type of artifact. And then there are baskets, which is the newest or youngest type of artifact. So what we see in this chart, Site A has 5 hand axes, 4 ceramic bowls, and no baskets. Site B has no hand axes, but it has 8 ceramic bowls and 5 baskets. Using just the numbers of artifacts from each of these sites, we can begin to relatively order them in time compared to one another. So the second type of dating in archaeology is called absolute dating. And absolute dating is putting an exact number on something. I want to talk about 2 methods of absolute dating, the first of which is called dendrochronology. Dendrochronology uses pieces of wood to reconstruct a sequence back in time. If you look at the word dendrochronology, chronology obviously means time, it has something to do with time, and then the word dendro refers to trees. So, Dendrochronology really literally means tree time. We call it tree ring dating. But we use tree ring dating to put exact pinpointed years onto archaeological sites. Our second method of absolute dating is called radiocarbon dating. This is probably the type of radiometric dating that more people are familiar with. In radiocarbon dating, we analyze the amount of certain elements that exist within the biological material of plants or animals that have died. And we can do this because as we go throughout our lifetime, as we breathe in and we breathe out, we breathe in the air that's in the atmosphere. There's lots of different elements in the atmosphere. We obviously rely on the oxygen that's in the air, but there's also nitrogen in the air and carbon. And there's a particular type of carbon called carbon-14. It's not very common, but it does always exist in very, very, very small amounts. So it exists naturally in our atmosphere. And when we breathe in every day, we breathe in some of this carbon-14. Carbon-14 is a radioactive element, meaning it is unstable. It does not like to exist the way that it is. It doesn't have a very sturdy chemical composition, and so it likes to decay into a different element, nitrogen-14. The way that radioactive elements decay is that every certain chunk of time, they lose half of their mass. So the half-life for carbon-14 is 5,370 years. That means that after every 5,370 years, a bone, let's say, will lose half of its carbon-14. And after another 5,370 years, it will lose another half. So only a quarter of the original carbon-14 will remain. This continues happening every 5,000 years. Half of that carbon disappears, half of that carbon disappears, half of that carbon disappears. So as archaeologists, if we find a bone, what we need to do is measure the amount of carbon-14 that remains compared to the nitrogen-14 and other elements within that bone. And based on the ratio of those elements, we can pinpoint exactly in time when that individual died. It's a very cool way to use chemistry to understand the passing of time in our lineage and amongst, in animals as well. There are a few other types of dating that employ similar methods, things like potassium-argon dating or argon-argon dating, uranium series. All of these measure the ratio of elements in rocks, and because they're in rocks, we can use them to date materials that are much, much older than bones like from humans or from animals that we would use radiocarbon dating with. All right, so we know how to date things in the past. We understand how to interpret superposition and the layering of rocks. But let's talk now about how we actually collect that data, how we go about doing archaeological fieldwork. The first thing that we do before any sort of excavation is called survey. And survey is where we basically walk around and we try to identify things on the landscape. We try to find places that will be interesting to dig. We try to find the relative frequencies of artifacts across a landscape, because often humans have some sort of place where they've preferred to live in the past, so they'll exploit one area of the landscape more than the other. When we do this landscape survey, we have a couple of techniques or a couple of strategies that we use, but mostly it involves just walking and looking at the ground. We use tools like cameras and maps to place ourselves in the geography of the area. We also use handheld GPS so that we can take exact location measurements of where we find certain important items. And we use things called total stations, which you can see this guy using here. You might see road crews using these same types of machines. They're very, very high resolution computers that are used in mapping things down to the millimeter. And so we use these to create very, very large maps of a broad landscape. After survey is completed, we'll identify a place to excavate. An excavation is digging into the earth to uncover the buried remains of previous cultures or previous civilizations. The excavation process can be very long and very, very slow. but it's how we get the most robust archaeological data. When we excavate, we do so in very, very controlled ways. So we set up an excavation grid. Basically, we string out a bunch of squares so that we can map in exactly where everything is as we find it. We also dig in very shallow layers. So we'll only dig down about 5 or 10 centimeters at a time, which isn't very much. 5 centimeters is maybe an inch and a half or 2 inches. So we'll only dig down a tiny bit at a time because, again, of that theory of superposition. The further down we go, the further back in the past we're going. So we dig slowly because if we take a big chunk out of the earth, then we're potentially confusing a big period of time. So this is very, very slow, laborious work, but it has to be, otherwise we're just destroying evidence that we can't get back later. As we dig, we have to record everything we find, every single artifact, every single bone. We record if the sediment changes as we're digging through it, and we use various tools for this. We use total stations again to map in all of the artifacts or bones that we find. We take lots of pictures. We use our field notebooks to record what's going on, to record our findings, to record our impressions of the site. We use things like trowels and brushes and screens to sort through all of that material and to very carefully excavate. We also use something called experimental archaeology. And this is where we try to replicate what people have done in the past today. So, for example, if we are studying a group of people in the past who hunted very, very large animals, it's going to be important for us to understand exactly how they did that. So perhaps we would get involved with butchering very large animals to understand the types of choices, the types of decisions that large animal hunters face when they capture this kind of prey. Or if you study stone tools, then one of the ways that you might experiment would be to make these stone tools yourself. And again, this is how we can better get inside the minds of people who lived thousands of years ago. When we try to recreate their technology, we can understand a little bit more about the circumstances that they were dealing with. All of the different sort of constraints or options that they would have had, and again, those choices that they had to make on a day-to-day basis. And by doing this, we can better understand how societies have lived in the past. Now, after we finish our research, after our survey, after our excavation, we still have to study all of the material that we've collected. Generally speaking, the things that we excavate from an archaeological site have to be kept in the country in which they were found. So we're usually not allowed to take things out of the country. And this is because of an unfortunately bad history that archaeologists have had of exporting things from countries and never quite returning them. So we try to make sure that everything stays in the country, which is a way of maintaining cultural heritage and also, building rapport with the people that we work with. It's good practice, it's ethical. When we do research in these countries, it typically happens at museums or research facilities or at universities. And one of the things that we have to do is publish the results of our research. Archaeology is a destructive practice. As you can see in this picture here, this is a big hole in the ground. And we can fill this hole back up, but we're never going to fill it up in the same way that it was originally laid down. So every time we put a shovel into the earth, we're destroying a little bit of the past. We're destroying a record of the past. So if we don't publish our results, we've essentially destroyed the past for nothing. So it is therefore our ethical responsibility to let the world know, to let the academic community know, and to let the broader human community know what exactly it is that we found. Otherwise, we've just destroyed cultural history for absolutely no reason. Like other fields of anthropology, we have a few ethical considerations as archaeologists and physical anthropologists. One, we have to include members of our host country in our research. This is, again, to build camaraderie, to build, to build this scientific community. And it also helps us avoid sort of newer scientific colonialism. We don't want to just march into someone else's country and say, we've got it from here, we're the scientists, so just leave us alone. No, we want people of all backgrounds involved in this research. And we definitely want people of the communities that we're working in to be involved, because that's also a way of ensuring that these individuals will be stewards to their cultural heritage. By involving people in their ancestors' history, we ensure that that material is protected in the future. We also have to respect all of the local laws and customs and traditions within the communities where we're working. It's obvious we can't break the law, but even things like being careful about the ways in which we dress. If there are considerations of modesty, then we have to make sure that we're dressing in a way that is appropriate for the place in which we're working. Sometimes that could mean a long sleeve shirt, or it could mean that women have to wear long pants and not wear, shorter skirts or shorts. We do this not because we're afraid of the repercussions if we don't, but it's a matter of respect. If you're working in someone else's country, you're working in someone else's home, there's no reason why you shouldn't give them all this respect that they deserve. This is still a sort of, it's a matter of cultural relativism, respecting other cultures and the values they have, even if they're different than the values that you have yourself. And finally, there are some heritage issues, meaning that there are some communities who are directly linked to the archaeological materials that we're studying. And this is certainly true of Native American groups in the United States today. So archaeologists, once again, have a not so fantastic history in the US when it comes to Native Americans. And there was a very poor practice for a long time of archaeologists finding Native American burial grounds and digging up those graves, taking the bones and all of the grave goods back to museums and just keeping them in museums. And this is very offensive. I mean, I think it would be offensive to anyone. But we also know that Native Americans are very attached spiritually to their ancestors, and so disturbing their ancestors' graves like this is an affront to their religion, and it's one of the most disrespectful things that you could do. Because of that, a law was passed in 1990 called the Native American Graves Protection and Repatriation Act, or NAGPRA. And this law says that if we ever find any Native American burials or any Native American skeletal material, we have to return that material to the tribe that it is from so that they can rebury that material. It also means that any museums who have Native American skeletons or who have objects that were originally in Native American graves, they also have to return that material to the appropriate tribes so that they can be reburied. This law caused a little bit of controversy when it was first put in place, but it's ultimately a really great step forward for repairing the somewhat contentious relationship between anthropologists and Native Americans, because it shows that we do respect the cultural heritage of people who were here before any of the rest of us, and people deserve to live their culture, they deserve to live their traditions, and they deserve to have their ancestors in the way that they intended.